Okay, hi everyone. Welcome to the fifth lecture. Today we'll be talking about pathfinding. This is a pretty important addition to your code if you want to start moving your robots deliberately from one location to some target location. So what is pathfinding? Basically, pathfinding is a way of getting from a starting location to a target location in an efficient manner. So I think a lot of what we've been doing so far is whenever you try to go from one location to another and you hit an obstacle, our strategy has just been move around randomly until we're unstuck and then keep trying to move wherever we're trying to go. And random movement can work, but it's inefficient and you can often get stuck moving around the same locations over and over again. We'll see an example of this later, but long story short, it's very inefficient and we don't want to be wasting bytecode. So that's why we use pathfinding.
Here are some common pathfinding algorithms you might be familiar with. The first one is breadth-first search, which just explores every name-during cell from the start location until we reach our goal. And the other one is A*, which uses a heuristic process to find the lowest cost path to our target location. Both of these are good pathfinding algorithms, but they have some problems for Battlecode. Because our bots have limited vision range, the BFS would have to calculate the whole path in our vision radius. And then they're also bytecode heavy, so the amount of turns that it would take to calculate the pathfinding algorithm would be longer than it would take to just move randomly and get to the location. So we would be wasting time analyzing all our paths. So we're going to introduce a more efficient algorithm.
Okay, so what we're going to be working on today is something called BugNav. Basically, it's, as the name suggests, modeled after how a bug navigates its environment. So basically, very similar to how bots have a limited scope in terms of what they can see, bugs are also very limited in their vision radius, right? So they can't obviously see the entire landscape. So basically what BugNav does is it allows our robots to make a decision or an attempt to get to a certain target location by making moves based on what it can see locally. And BugNav has a lot of advantages over the traditional search methods like BFS and A*, but some caveats are it's not always optimal. So for example, BFS, I can guarantee you that if there's a way to get from the starting location to a target location, then BFS will find the optimal solution. With BugNav, that is not always the case, but it's usually pretty good. And most of the times, all we care about is getting a pretty good solution. So as long as we know that there's a path from point A to point B, we just want to know that we can get there somewhat efficiently, but we don't have to waste bytecode on computing the exact optimal path. And then another issue with BugNav is, as we'll see in one of the variations of BugNav, the bot might start looping, which is not ideal, but we'll see in variants 1 and 2 that we can fix that. Okay, so Bug 0 is the first algorithm that we'll look at, and the general idea is that we always start moving in the direction of our target or our goal, and whenever we hit an obstacle, we will kind of trace along the boundary of the obstacle until we're unstuck and can move again in the direction of the goal. So in the picture, for example, you can see we start off by moving northeast towards our goal, but then we hit the obstacle, and so what we do when we hit an obstacle is we can start rotating left until we're able to move again. And in Robot Controller, you have the ability to rotate left, right? We have a rotate left method for directions. So, and I think it's in increments of 45 degrees, so you can just incrementally rotate leftwards until you can once again move in the direction. that you're facing. And then you'll take a step forward, and then every time you take another step forward, you have to like reevaluate your direction towards the goal. And we'll go through an example in a minute. Okay, so bug 0 is really easy to implement, but one issue is that your robot can get stuck in loops, as we will see, and never make it to the goal, so you'll end up with like a really useless robot. But we'll show like one successful attempt and one failed attempt. So yeah, so I guess we can start coding now. Okay, so here I have the example funcs player that you all have access to, and we'll just directly modify this. Okay, so the first thing I'm going to do is I'm just going to simplify the code so that we can kind of isolate the algorithm that we're looking at. So let me just get rid of some of the methods here. Okay. So also another thing I'm going to do is I'm going to make sure that we only work with one robot per team so that it's easier to kind of like examine like what the robots are doing. So first, actually, I'm going to show you guys the map that we're going to be working with today. It's like a pretty simple map, but it'll like kind of highlight the advantages and disadvantages of each strategy. So lecture map, example funcs player.
That's good.
Hold on.
You just run it with the lecture player for now, so they can see the map.
Okay.
Yeah.
Oh wait, actually, I'm going to reset example funcs player. Okay. Okay, yeah, so here you can see. Okay, here you can see the map that we're going to be working with. We're only going to have robots spawning from the paint towers in the upper left and bottom right corners. So let's just modify the code real quick to do that. Okay, so the way I'm going to do that is every time we call run tower, we're going to get rid of all the functionality from building the different types of robots. So actually, we're going to simplify this a lot by just building one soldier per money tower, or per paint tower. So we're going to get rid of this. Get rid of messages for now, too. Okay, and we'll keep the random like spawn direction for now. Okay, so the way that we can make sure we only spawn one robot per tower is I'm going to introduce a static variable here. Or yeah, so static boolean has spawned. And that's going to start as false. And every time our tower spawns a soldier, we are going to say has spawned equals true. And then in our try statement, we will check, okay, so the first condition is we want to make sure that this tower is a paint tower, right? So if rc.unit or get type equals unit type dot level 1 paint tower, because they all start at level 1. And we also have to check that we haven't spawned before. So then we can call run tower. Okay. And then otherwise, I guess for right now, what we can do is just like, since we only have soldier robots, if our unit type is soldier, we can just do something simple like, let's just move in a random direction. So we'll take this code here, just generate a random direction. And then if we can move in that direction, then we'll just move. So this is just to see what we're working with. Okay, yeah, cool. So we just have one robot and it's moving randomly. And as you can see, like in a map like this, it's very likely that your robot will just get stuck if it takes random actions. I think eventually one of them should escape. Yeah, okay, so the gold one eventually makes it out of like its corner, but not very good, right? So that's one reason that we're gonna use pathfinding as opposed to random movements. Okay, so now to implement bug 0, let's create a new method. We're gonna call this bug 0. Okay, so the first step for basically all the bug algorithms is you want to try to move in the direction of the target, right? So we have to get the target direction first. So we'll just say direction that we want to move in is, and the way we do that is we get our current location and we say direction to and target. And we're gonna have to define a target as well, but I'll do that a little bit later. Okay. Then we check if we can move in that direction, right? So if rc.can move there, so if we can move, we just directly move in that direction. Otherwise, what we want to do is what we were talking about earlier with the rotating left. So the way we do that is, since we can rotate 45 degrees to the left with every call to rotate left, the maximum number of times we're gonna have to rotate or call the rotate function is 8 times. So we'll say like, we'll do a for loop for int I equals 0, I is less than 8, x plus. So we'll take our current direction and we'll rotate it by 45 degrees to the left. And then we can check once again if we can move in this new direction. And if we can, then we'll move and we should break out of here because we don't want to keep rotating after we're able to move. So I think this should be good now. And we just have to define a target. So as I said, we'll look at 2 different scenarios. For the first one, let's just look at the upper left corner. So let's say we were trying to get to 0.29, right? So let's define a target. Static map location target. I'll actually initialize it inside of run. So target equals map location. And I think it was 0.29. And this time, so I'm just gonna modify the run function now. So instead of taking a random movement, let's call our bug 0 algorithm. Okay. Let's slow this down. Okay, but as you can see, it worked. I'm gonna start it over. Okay, so yeah, this is one instance where bug 0 works really well. I mean, the silver robot didn't have to do anything, but the gold robot like tried to move to the upper left corner, got blocked by the wall, and then kept rotating left until it could move again, and that's how it circumvented the obstacle. And actually, I'm gonna add some indicator dots, so that we can more clearly see what's happening, and this will be more important for the next part, but the way we do that is, let's see, where is it? Okay, bug 0. So let's place an indicator dot on the location that we're trying to move to on each step before we do the rotation. So we can define like a map location called like, I guess, next location equals our current location. And then we want to add the direction that we're moving in, that we want to move in at least. And then we can place a marker. So, or not a marker, indicator dot. Yeah, so next location, and it's just RBG values. We're gonna do, okay, so we're just gonna pick red. Okay, this, oh, actually another thing is it'll be easier to visualize if we call clock.yield first. This will just make sure that like the dot shows up before we move to the location, so it'll make more sense. But yeah. Okay. Yeah, you can see like the red dot is on the wall, right? Because the robot is trying to move in that direction, but it can't, so it rotates. So this is one instance where it works, and then I'm gonna show an instance where bug 0 is not so great. So we're gonna change target. Okay, and this time I'm going to make 2 different targets, and it's going to be the 2 ruins. So actually, like, we can't be on a ruin, so I'm just going to make it the locations next to the ruin. So for example, like, this way they're not like fighting over one spot. If c.team.
(11 and 13).
Okay.
(18 and 16).
Okay, so the goal right now is to get the robots to like these, I think you can see it, yeah, these 2 locations. And let's run this. Okay, so this is still bug 0, right? So as you can see, both of the robots are getting stuck, right? They're just like walking back and forth between the same 2 spots. And to see like why this is happening, let's focus on the gold robot. So for example, okay, so when the robot is here, it wants to move north, right? Because that's basically like the best direction it can move in to get towards the ruin. So it's gonna move there. The next place that it wants to go is like northwest, right? But there's a wall, so it can't. And so what it's gonna do is it's gonna keep rotating left, and eventually the first time that it can actually move is when it's facing south. So it's gonna move south, and so on. So it's just gonna get stuck. So I guess what you can see here is like bug 0 is pretty easy to implement, and it can work in some cases, but it's kind of risky because if you end up with a map like this, you'll just have one useless robot that's like circling the same small area over and over again. So that's why we're going to talk about another variation of bug nav. Okay, so next we're going to talk about bug 1, which is pretty good. It's an improvement over bug 0 because you will no longer, like you're guaranteed to be able to make it to the target location. So you're never going to get stuck. The drawback is that you will see it takes, in some cases, significantly more time to make it to the goal than bug 0. But basically the idea of bug 1 is that every time we're blocked by an obstacle, Instead of just kind of tracing along the contour until we can move again, we're going to trace the entire obstacle once, find the location on that trace that is closest to the target, and then we are going to go back to that location and then go towards our goal. Yeah, and as I said, this guarantees that you will reach the target as long as there is a path from your location to the target. Okay, so let's code that. Okay. So I guess the first thing that we need to take care of is there's kind of two modes that we'll be in, right? So one mode is tracing mode, where we're like circling. So like every time we hit an obstacle, we're gonna have to trace it. And so there's a tracing mode, and then once we're done tracing and we find the location that's closest to the target, we're back in like non-tracing mode where we can move normally again. So first, we have to define a static variable. It's going to be a Boolean variable, and it's going to be is tracing. So this will tell us like what mode we're in. And it's going to start as false. Okay. So now let's look at bug one. Okay, so first we should check what mode we're in, right? Because that dictates like how we make decisions on where to move. So if first we check if we're not in tracing mode, is tracing. Basically, if we're not in tracing mode, we want to like try to move towards the target. Okay. And then if we are in tracing mode, we don't care where the target is, right? Like all we care about is staying as close to the obstacle as we can and circling it. And we want to like keep it on our right-hand side if we're circling it clockwise. So I guess circle the obstacle, ignore target direction. Okay, so first, let's just assume we're not tracing. So the first thing we want to do is, as always, try to move towards the target, because if there's nothing blocking us, we can just move towards the target. So I guess we should define the direction first. So direction, it's pretty much the same as bug 0 at the beginning. Or I guess we don't have to do the indicator stuff. Okay. Yeah, so we'll check if we can move. Move. Then we just move. Okay. However, this time, if we're blocked by an obstacle, we're not going to just keep rotating, right? Like we want to be smart about this, and we're going to circle the obstacle. So what we're going to do is we're going to go into tracing mode. Okay, so first we'll set is tracing equal to true. And then, okay, so another thing we need to define is a tracing direction, right? Because when we're tracing, we're no longer interested in the direction of the target. So we're going to introduce another variable, and it's going to be a direction called tracing direction. And I guess we can start that at null, because it's meaningless when we're not tracing. Okay, so once we enter tracing mode, we'll initialize the tracing direction to be the direction of the target. But that's just to start. After that, we're not interested in the target direction anymore. Okay. Okay, now, so next we should take care of the case where we are tracing. And I think, okay, yeah. So when we're tracing, we need to establish like a stopping condition, right? Because we can't trace forever. So the way we're going to do that is we will stop whenever we reach a location that we established earlier is the closest location to the target. So let's implement a check for this. So Okay, yeah, so what we need to do is we also need to, while we're tracing, we need to keep track of the closest distance to the smallest distance from our trace to the target and also the location on our trace that's closest to the target. So let's introduce more static variables. We can do closest, or let's call it smallest distance. And we should like make it something really big so that we're guaranteed that we'll update it on our trace. Okay, I think that should be bigger than any distance on the map. And then we also need a location, right? So this will be closest location, like closest location to the target. And that will start as null. Okay. So what we can do is we can check. Yeah. We should check if our current location is the optimal location. So if rc.get location, and here we can use the dot equals, right? Because we want to compare the x and y values of our location. So dot equals, what did I call it? Closest location. Okay. Yeah, so if we are at the closest location, we can stop tracing. So we'll set is tracing equals false, and we should reset all of our static variables because these like don't mean anything anymore until our next trace. Okay. So next, if we're not at the closest location, what we want to do is, that means we're still like tracing and trying to find the closest location, right? So we want to keep checking if our new location is like the new closest location. So we have to check if our current distance from the target is smaller than the running minimum distance. So we can do that by doing, let's just say, let's call our current distance to the target current distance, and we'll get location and distance squared to the target. Okay, so then if our current distance is less than the smallest distance that we've found so far to the target, we need to update, right? So our smallest distance will be current distance, and then our closest location will be our current location. Okay. Cool. Okay, and then we also need to, of course, implement logic for like moving around the obstacle. So the way we're going to do that is, first, we want to always like try to move forward if we can move forward. And we're going to assume at any point that we have the obstacle on our right-hand side. So the first thing we do, and we're going to like make sure to take care of this in our code, right? So at the very beginning, when you hit the obstacle, you're going to be facing it head on. But we're going to implement our code so that you like make a left turn so that the obstacle is on your right-hand side. But I guess the first thing we can do is if we can ever move directly in our tracing direction, we're going to move. And one important thing is that as soon as we've taken a step, we have to make sure to rotate right. And the reason is we want to keep the obstacle on our right-hand side, right? So let's say you have the obstacle on your right-hand side, you take a step forward, but maybe that was like the corner of the obstacle. So we always try to move right if we can. So if we took a step forward, we have to make sure to rotate our tracing direction. And we're actually going to do this twice, just because the rotates only by 45 degrees, and we're not going to have a wall that's like at a 45-degree angle. So all the corners are 90 degrees. So we'll rotate right twice. Okay, now if we can't, so like, as in the case when we first hit the obstacle, we can't move straight forward. So what we're going to do is we are going to rotate left, I believe. Yeah. Yeah, we're going to keep rotating right until we can move. So again, it's very similar to what we saw before. We're going to update our tracing direction by rotating left. And then we will check if we can move in that direction. Sorry, can move. Okay. Yeah, so we're gonna keep rotating left until we're able to move again. And at any point, if we are able to move, we'll take a step. And then once again, you have to take care of the rotating right, or else you might end up like straying pretty far from the obstacle. So we want to make sure that we like stick as closely as we can to the obstacle. So we'll rotate right and then make sure to brake so that we're not like endlessly rotating. Okay, I think that should be it. Okay. Oh, I have to implement bug 1 now. Okay, so let's switch this to bug 1 and let's see what happens. I guess right now the target location is still what we had before with the 2 ruins. Okay, yeah, as you can see, it's like tracing out the entire perimeter of the obstacle before making any deliberate move towards the target. But yeah, you can see like they both successfully reach the target. It just takes a little extra time. One thing, like if we switch the target, for example, to okay, let's switch the target back to the top left corner. And you'll see that they should both get to their target location. It's just kind of annoying because, like, as you can see with the gold robot, it's like doing a lot of extra perimeter searching before actually like deciding to move towards the target. And so like bug 0 was really efficient with that, but obviously with the trade-off of getting stuck on the ruins, like when trying to reach the ruins. So I guess you win some, you lose some. But yeah, that's pretty much it. Okay, next we're going to introduce another version of the bug algorithm.
Okay, so now we're going to introduce bug 2, which is similar to bug 1, but instead of looping around the object, we're going to draw a line from our target to our goal. And whenever our robot intersects the line, we are going to follow the line to our goal. Right. Gone to the code. Oops.
Oh, sorry.
Okay. All right, so the implementation is very similar to bug 1. And for the line calculation, I'm just going to copy an algorithm called Bressen's-Ham's line algorithm, which just looks at the positions in the map and converts them into a hash set containing all the grids that are intersecting the goal location and the start location. So put this over here. And then we have to import our hash set. Okay. So we're going to define our bug2 function. The first thing we want to do is define our line from our goal to our target location. So if our target location doesn't equal our previous target location, we are going to create our line function. So we're checking this just in case we change our target location, because each time we change our target location, we're going to want to update our line, because from the goal to the target, it'll be a different line each time. So we're going to update our previous destination to be our target location, and then we're going to create the line from our target to from our current location to the target. We're also going to have to define our static variables for our line, which will be a hash set of map locations. This will just store all our grid positions for the line. And so once we have our line, we also want to define our previous location. Okay, so once we have our line, we want to check if we're tracing or not, just like in bug 1. And we're going to implement essentially the same behavior from bug 1. So if we're not tracing, we want to move in the direction towards our target. So and if we can't move, we want to initiate our tracing. And then we also want to have a variable to measure the distance from the start of the object, the start of the obstacle, till our trace line. So we make sure that we always clear the obstacle and don't, once we collide with our line, we don't go back towards the obstacle. So and we're also going to define that as a static variable. Okay, so now if we aren't tracing, we want to start tracing, but whenever we collide with our line, we want to follow the path. So if we first want to check if the point that we're at is on the line, and we also want to check if we have cleared our obstacle. So we want to check if our location from the distance to the target is smaller than our obstacle distance. So then we make sure we clear the object, and sorry, distance greater too. Okay. So if this is the case, we want to stop tracing and go back to following our line path. So we're going to set tracing to false. And then if we haven't collided with our line, we are going to start tracing around our object. So just copy from bug 1. Okay. And that should basically be it. Run and see how it works. So now you can see, oh, I haven't changed the movement choice. Oh. It's a bug too, so we can see the behavior as the robot moves. Okay, so now the robot should trace along until it finds the line that intersects with our target location, and then it'll follow the line and reach its target location. So let's put the ruin on so we can see it get to the ruin. And I'll also add indicators so we can better visualize the line and the steps it's taking. And we'd add the same indicator for the line. So for each map location on the line, we're going to add the map indicator. So now we'll see the line that intersects with our target destination, and we also see the way that the robot takes the path. And as you can see, this is way better than bug 1 because it doesn't loop around our obstacle multiple times, and instead it takes not necessarily the shortest path to our location, but an efficient enough path to where it doesn't waste turns looping and looping. So that's it for our pathfinding lecture. We'll be staying here for office hours, and if you have any questions, feel free to send them through Discord. And there are also other pathfinding algorithms that you could implement, but we leave that up to you to figure out what works best for you. All right, thank you.
Thank you.